Hello, and welcome to my lightning science talk. I'm Corry L, and before we get started here, if you have one around, grab a balloon and blow it up. We'll use it later in the talk. If you don't have one, no big deal. You will manage anyway. So I like to make my talks a little interactive, so there's going to be some interactive components. Unfortunately, I'm not going to be able to see you, so we'll just do our best. This is ZAP, Lightning Science, and I am Corry L, your host. I have a PhD in physics, and so some of that is going to come through in the stuff I talk about, but I've designed this talk to be accessible to everyone. So whether you have a PhD in atmospheric science or you have last thing you learned about science was in public school, like, that's totally fine. I'm super glad you're here, and I think you'll learn some cool things. So let's get started. As a little bit of trivia here, medieval European church bells, well, okay, so backing up just a second here, people didn't used to know very much about lightning. There were a lot of lightning gods or gods that were related to lightning. It was very mysterious, kind of terrifying, and one example of that is in medieval Europe, a lot of church bells carried the inscription Fulgara Frango, meaning I break up lightning flashes. And there was a job that some people had, which was to ring this bell during lightning storms because they thought that would help make the lightning not strike them and burn up their town. But so the job description goes like this: pull on this wet rope connected to a metal bell, the highest point in the landscape during a lightning storm. As you can imagine, given what we know now about lightning, that was not a very safe job. There's a 18th century German book that cites 386 church steeples struck in a 33-year period and 103 bell ringers dead while performing their duties. So I'm glad we know more about lightning now. Let's talk about why that's dangerous, what lightning is, all sorts of good stuff like that. And first, a lot of people think about Benjamin Franklin when they think about lightning. Let's talk about Benjamin Franklin's original experiment, because science is not always like, bam, I figured it out right away. So Benjamin Franklin's original experiment is drawn here. And there's a picture of a person holding on to a metal rod that sticks up into the sky. And Franklin's idea was that if this person grabbed this rod during the lightning storm, and this is actually electricity going on, because people didn't know, people had been kind of playing with electricity, but they didn't know that lightning was electricity. So they're like, okay, this person grabs this rod and they stick out their hand. You can see there's kind of like lines coming from that person's hand. It's because Franklin thought that there'd be like cool like sparks that would come from this person's hand if they grabbed this in a lightning storm, and this was really electricity. So my question for you, the audience, is this experimenter in danger? Yes, don't grab that rod, or no, yeah, experiment for science. So think about your answer, and the answer is yes. That experimenter is in danger, and they should definitely not grab that rod. Some people performed this experiment, and there was somebody in 1752, Thomas François d'Alibert, who successfully performed it and didn't die. But then the next year, there was a Swedish physicist who did try it. The rod got directly struck by lightning, and this poor person died. Franklin, as far as we know, did not ever perform this experiment, but did the one that we're all a little bit more familiar with the kite flying up into the lightning storm and getting struck. And one thing that's important about this is this kite string is conductive, but there's like this insulating silk string at the very end that protects Mr. Franklin from being torched by his experiment. The idea there was that there's this key dangling off the line, and it zaps and makes cool sparks. And all of this experimentation around lightning and trying to figure out what it was actually led to the very first practical application of electricity study. And so people started putting lightning rods on buildings in 1752. And this is where you kind of stick a metal rod up from the top of your building, and it connects via wires or metal pipes or something metal down into the ground. And so if that building gets struck by lightning, the lightning has an easy path where it can flow. The electric current ends up in the ground instead of ends up burning up the house. The next application of electricity didn't actually come for about 50 more years when Volta invented the electric battery. Okay, so another little fun application of electricity here. Sometimes people actually made accidental lightning rods before anyone knew what lightning rods were and that they were a good thing. And here is an example of St. Pierre Cathedral in Geneva. And this tall cathedral here is metal clad. So it's sheathed in copper, and it sticks way up higher than anything else in the landscape. And so it's kind of a beacon for lightning. And while it has been struck many times, it has not actually historically suffered damage. These two bell towers on either side of it, however, have, because they are not metal clad. And this big tower actually has like metal drain pipes and stuff that go all the way to the ground. So it was actually very, very safe. All right, let's talk about static electricity. So if you grabbed your balloon at the start of the talk, awesome, get it out. If you have one handy, you could run and grab it right now. Blow it up and rub that balloon on your head, on your sweater, and play around with it a little bit. Can you make your hair stand on end? You can also rub it on your arm if you don't want to mess up your coiffure like mine. And just play with it a little bit. Like, do some materials work better than others? What can you, if you rub it on the head and you stick it to something, can you get it to stick? And like, so what's going on? If you don't have a balloon, cool, no worries. Maybe you can play with one after the talk. And I'm going to show you a balloon simulation. This is through PhET, which is PhET. You can pull it up later if you want, phet.colorado.edu. This is the University of Colorado, has a bunch of physics education simulations. And this is one of them. So here I've got my balloon. I'm going to rub it on my sweater. Oh yeah, that sweater is so good, wool, wool, wool. And when I started out, right, this balloon has some positive and negative charges on it because it's made out of neutral atoms. My sweater is the same way, positive and negative charges. But this balloon, oh, it sucks up all those negative charges. It's great. And now, when I release this balloon, it sucks itself to the sweater because opposite charges attract. What happens if I bring this balloon over to the wall? So ask yourself, think about it for a minute, what's going to happen? Bring it over to the wall, over to the wall. You can kind of see what's going on here. Oh man, if it's really close to the wall, you see how those negative charges in the wall are being pushed away from the balloon? So it's actually leaving sort of some positive charge here close to the balloon. And if I get the balloon nice and close, like touching up against the wall, it can actually stick because all of these negative charges are attracted to these positive charges since we've pushed the negative charges away. Keep this in mind. We're going to go talk about how this relates to lightning. So first, let's talk about where those charges come from. I gave you a little bit of a preview earlier on. Stuff is made out of molecules, which contains atoms. And inside those atoms, here's sort of a blown up of an atom. Inside those atoms is this nucleus. And inside this nucleus are protons that have a positive charge, these red ones, and neutrons that have no charge. The protons are what we're interested in, this positive charge. And surrounding that nucleus, we have a bunch of electrons kind of fuzzing around in a cloud. So atoms typically have the same number of plus charges and minus charges, so they're neutral. They have no net charge. But the energy that we get from rubbing that balloon on our head or on the sweater or whatever, that can knock electrons off, leaving on the sweater some positively charged ions. Ion just means it's something that has a charge. And on the balloon, we end up with all those spare electrons. The rubber of the balloon likes to suck up some spare electrons, which means that we have negatively charged ions on the balloon, positively charged ions on our sweater. They can stick together again with that like charges attracting. So, okay, how does static electricity relate to lightning? Here is a picture of a couple of I would say rather foolish people who are having their hair sticking on end when they're out on the top of a bluff in the middle of what is either a lightning storm or is about to be a lightning storm. So spoiler to the part of the talk where I'm going to talk about lightning safety, if your hair starts to do this, you should not be standing on the top of that bluff. You should get down and not be the tallest thing in the landscape. But so here's a little suggestion that static electricity, like we did with that balloon, is related to lightning. Before I connect those dots, let me just ask you a question and teach you a little vocabulary. So which of the following words is used to describe a type of weather? Normally I ask this talk with colored cards and I have you vote in the audience, which is why there's color names there too. But just ignore that for now and look at the words. So which of these describes a type of weather? Is it grapple, emesis, syzygy, or astroblem? Dun, 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 make your choice. Turns out it is grapple. So grapple is soft hail. These are all actually science words, which are kind of fun. Emesis is the act of vomiting. Syzygy is being joined or aligned. It's kind of an astronomy term. And an astroblem is an eroded remnant of a large ancient meteor crater. So, but grapple is the one that's useful for us. Why? Well, collisions create ions and thunderclouds. So what we know right now of how thunderclouds get electrified so that they can create lightning is this. Grapple, these soft particles of hail falling down in the cloud, and ice crystals, frozen water crystals, are rising in the cloud due to the temperature differences up there. And just to note, even in the summertime, the temperatures up in the clouds are pretty low. So you actually have this grapple and these ice crystals, even if it's not, pardon me, even if it's not going to like snow or hail. Though it can hail, right? Like hail in thunderstorms is actually somewhat common. Anyway, so the grapple and the ice crystals bashing against each other kind of do like our balloon on our heads and trade electrons. So you end up with grapple with a negative charge falling downward and ice crystals with a positive charge flying upwards. One thing that's kind of cool is that depending on the temperature up in the clouds and around it, the plus and minus signs can flip. So this is the state for most thunderstorms, like your standard summer thunderstorm. But like if you've ever been in thunder snow, like a winter blizzard that has lightning in it, the signs are typically flipped there. Okay, so that grapple balloon charge basically results in a thundercloud like this one here. Whoops. So you have the negative charges all end up at the bottom of the cloud, the positive charges all end up at the top of the cloud. And like when we brought that negatively charged balloon up close to the wall and it pushed the charges in the wall away, that's kind of what's happening here. The negative charges in this thundercloud are pushing the negative charges in the ground away. You can see them kind of over here on the edges, and you end up with just this positive sort of charge beneath the cloud. So, so this is kind of the situation of the thundercloud. Negative charge at the bottom of the cloud, positive charge on the ground. Now, let's connect static electricity, this little kid with the fun hair on the slide, and dynamic electricity where you've got sparks and lightning and such, like in this kind of goofy drawing. First, let's talk about current. So water flow is kind of a good analogy for the current flow of electricity. So let's first talk about water, because we all have a pretty good understanding of what that means. So in a river, you have higher elevation and a lower elevation, and the water wants to flow downhill, right? It goes from higher elevation to lower elevation. There's this height difference, and it results in water motion. It's kind of what happens in wires or electrical, where places where electricity flows. There's, instead of a height difference, there's a voltage difference that's created by positive charges on one side, negative charges on the other side. And that results in electrons moving, typically through a wire. And the motion of those electrons is kind of like the water flow in the stream, and it results in current, which we can use to run our computers or our coffee makers or whatever. All right. Let's talk about electric breakdown. Oh, this little thing that is hidden behind my head here, reminder of our cloud, right? So this is creating the voltage difference that we're interested in for a current flow, the bottom of the cloud to the ground. Okay. So let's talk about electric breakdown. When you have a cloud and you have the ground, there is no wire between them, right? There's this big air gap where my head is sitting, and like lightning ends up bridging that gap, but what's the deal with that? So air is normally a really good electrical insulator. Like when you have your coffee pot, like there's wires running through it, but there's not like sparks zapping all over the place unless there's something seriously wrong with your coffee pot. So air is normally this great electrical insulator. Its molecules don't like to give up or take electrons. But if you have enough energy, if you rub that balloon really, really hard and you get that voltage difference really, really high, you can actually get a spark, right? Or if you're like walking on your slippers and you touch the doorknob, you get a spark. That is the case where there's enough energy, there's enough voltage difference between your finger and the doorknob that you actually break down the air in between it and you tear off electrons, and it basically ends up that ionized air ends up acting like a wire through which current can flow. So here's lightning. Really back to lightning. Promised we'd do it. So lightning begins. Why is this not beginning? Oh no. My animation is broken. One moment. Let me pause this recording and figure out how to fix it. All right. It doesn't want to play in the slideshow, so we're going to watch it here and then return to the slideshow. Here is lightning beginning. This is called a leader. It's also called a stepped leader. So what's happening here is an ionized channel of air is created right at the top of this thundercloud. And the weird thing is we don't actually know why it starts. So the very beginning of lightning, we don't understand. The electrical difference between the top of the cloud and the ground is not actually enough to get that spark started. So like the difference, like this thing that you get from rubbing your feet on the ground and like reaching to your doorknob, that spark that's created is created because there's a voltage difference between your finger and the doorknob. The voltage difference between the cloud and the ground, not big enough to start the spark, but somehow the spark starts. And you can see from this image that it's kind of like going in jerks, right? It's a little bit like it starts going and then it stops for a little bit. It starts going and it stops for a little bit, kind of like cars stopped at a stoplight. And what's happening here is that the current, the electrons that are flowing, they kind of flow, they ionize some of the air, like they get this little spark happening, but then they like kind of run out of juice. So they stop, and then more electrons flow from the top of the from the bottom of the cloud down into that channel, and then it's enough. It's like water pushing up against a dam, and then it bursts through, and it ionizes another little chunk of air. And those little chunks of air are like 45 meters long, so they're really big, but a thundercloud is really far up above the ground. So it takes a number of these little spurts, and it's sort of spreading out because those cars at the stoplight are like trying to find a good way to ground, and like maybe it's over here and maybe it's over here, and so you get this like kind of spreading out thing that we associate with lightning from this stepped leader kind of looking for the best path to ground. Now, what happens next? So next, I'm going to show you, well, first I'm going to show you a video of this stepped leader because it's cool. And if we use a super high-speed camera at 100,000 frames per second, we can actually watch this step leader in action. So it has kind of some goofy music, but check this out. So these are the stepped leaders, like actually in process, doing their thing. So you see that they're kind of going before you get the major flash, and that major flash lasts a lot longer than the stepped leader itself. Okay, so this talk. This is on Planet Slow-Mo. If you want to watch it, watch some more of it. Okay, so then what? We have our stepped leader, and all right, I gotta just make myself a little smaller here. So I mentioned before that like charges attract, and remember that the base of the thundercloud has this negative charge, and the ground beneath it develops a positive charge. And, oh, sad animation. Okay, so here we're gonna watch the animation go. When the leader, this red line coming from the cloud, approaches tall objects, you can see this little blue thing is starting to grow up from this antenna sticking up from the building. So as this leader grows down, the voltage difference between the end of that leader and the ground increases. And that's where you really get that kind of like doorknob finger spark. But you actually get the spark coming up from both directions. It's coming up down from the cloud, but also up from the buildings. And if this animation were a little bit more realistic, we would actually see those leaders coming up from all of these tall locations. When those leaders finally connect, that's called the return stroke, and you get a bunch of current flow. That was in the video we saw, the like bright flash that lasted longer. And we can see this in an actual photograph. So this is a photograph taken with a slow motion camera. And here's the stepped leader coming down in these frames as time advances. And you can see at the top of these buildings, the upward, the streamer coming up from the top of the buildings to meet that leader coming down. And then they connect here at the end in that final big discharge. Well, okay, so we managed to connect the leader with our streamer, and lightning, it turns out, is more than just a single flash. So to kind of put all the pieces together that we've built up, this return stroke after the two leaders connect is a bunch of current flowing down that sort of wire that we've created by tearing the electrons off the air. And it's totally crazy how much energy is flowing in that. The temperature of that path, that sort of wire that we've created through the air, is 30,000 degrees Kelvin. That is 5 times the temperature of the surface of the sun. 5 times! Holy cow, right? And there's a bunch of current that flows too. If you like numbers, they're there. And another thing that's really cool is after that main return stroke, additional charge can often be pooling up there in that top of the cloud. And it says, oh, hey, like, I don't want to have to do the work of creating this leader myself. I can just flow down this path that has already been built. So a lot of times, after that first return stroke, that's like the brightest and the biggest, but then you'll often get more flashes as a little bit more current kind of collects, and then it bursts through, and it collects and it bursts through. You can have up to 20 of those. The average is more like 2 to 3. And so if you've ever watched a lightning storm, and the lightning sort of seems to flicker when you're looking at it, that is actually happening. The human eye is fast enough that it can catch the flickers as those multiple strokes of lightning occur. How cool is that? You can also photograph this. This is an old school way of doing it where you like roll the film past the camera really fast. It's called a streak camera. And so here you can see this one, I don't know, has like 12 or something streaks. And this first one is the biggest and brightest. And it's also the one that you can see the forking from that leader. The other ones, the other strokes after that first one, they don't need to follow that forking path because there's already this like strong wire of ionized air for it to flow down. You can do this nowadays with your camera if you put it on something that makes it jiggle back and forth. There's some cool photos that people have taken that way. Okay, now let's talk about where lightning happens. Here's a picture of the globe. And we can see that there's kind of some patterns here, right? Like lightning seems, let me explain the scale. So dark blue, like here where I live up in Seattle, dark blue to white, there's hardly any lightning. This is the average number of strikes per kilometer per year. We have a really sad dearth of lightning here in Seattle. As you get into the red and the orange and like bright yellow, like here, those are getting into the hundreds of lightning strikes per kilometer per year. And we see a trend here, right? It happens over land, and it typically happens over warm land because the sun heats the surface of the earth, and that creates the right kind of convection for us to ionize these clouds and get the situation for lightning happening well. Okay, so that's Earth. what about other planets? And here's another quiz for you, or not quiz, but think about it. Where do you think we have observed lightning? Is it only on the Earth? Is it the Earth, Jupiter, and Saturn? Is it the Earth, Jupiter, Saturn, and Venus? Or is it Earth and all of the gas giants? Think about it. Think about your answer. And if you said the Earth plus Jupiter and Saturn, you are correct. If you said the Earth, Jupiter, Saturn, and Venus, you're probably also correct. We have directly observed lightning on Jupiter and Saturn. We have indirectly observed the electrical signals that look like they probably came from lightning on Venus, but on our flybys, we haven't actually seen lightning. So I think there's probably lightning on Venus, but it definitely happens on other planets. We don't have enough information about extrasolar planets to know whether lightning's happening there too, but yeah, it probably is. Okay, let's talk about lightning dangers and injuries. I sound very excited about that. I don't want people to get hurt, but it's kind of interesting. So heads up, don't stand under this tree. This tree is out in the middle of nowhere, very much the tallest point in the landscape. It is just begging to be struck by lightning. All right, here's a couple diagrams from XKCD What If comic, which is fun. It's about lightning. And here you can see the sort of the old school thing that us somewhat older folks learned of, like, don't be talking on the telephone during a lightning storm. That's because lightning can follow this path to ground. If it strikes your house, it wants to run down to ground, and an old school telephone line can give it that. So can water pipes. So you don't want to be like standing in the bathtub during a lightning storm. And similarly, standing in a waterfall, not a great idea. For all those times you're standing in a waterfall in a lightning storm. Also, an open boat on the water is pretty dangerous because your head is sticking up and it's making you kind of the tallest point in the landscape, so you're likely to get struck. If you're in an enclosed boat, though, you're about as safe as you are in a car, which is pretty safe because the lightning will tend to run along the outside of the car or the boat down to the ground. Submarines, actually, quite safe, as are marine mammals. Lightning hits the water and spreads out, which we will talk about here. So when lightning strikes water, I've given a list here of resistivity, which is sort of how resistant a material is to letting current flow through it. So we talk about conductors and we talk about resistors. Conductors are things that like to let current flow, like things at the top of this list like copper and seawater are pretty good conductors. Then there are things that are resistors. Things that are really good resistors are things like air and wood, especially dry wood. And then like drinking water, it's fairly pure. It doesn't have a lot of ions that want to let current flow, so that's kind of in the middle there. Human skin is also kind of in the middle there. So one thing to note about conductors is that current travels along the surface of conductors. So when this lightning strike happens, hitting this pole here, it's going to kind of spread out on the surface of the water rather than going down deep into it. So, and when it spreads out, it can actually spread out to a pretty good radius, about 20 feet radius near where that lightning was struck. And so things that are kind of sticking up out of the water, like if you're in a swimming pool and your head's sticking up in the water, but like the strike doesn't hit your head, cool, awesome. But if it hits kind of nearby you, it can spread out along that surface of the water and then like go into your head, and that's not good, which is why we want to get out of the swimming pool in a lightning storm. Turns out sound from the lightning strike is actually also dangerous and can kill fish. It's 260 decibels at 1 meter away from the lightning strike, and a jet engine at takeoff at 25 meters is 150 decibels, which is like a lot lower, but can still cause your eardrums to rupture. So lightning, it's loud. Or I guess the thunder, it's not what we call the lightning, the flash that's loud. As I mentioned before, because that lightning doesn't penetrate very deeply, marine animals that are submerged are usually pretty safe. Okay, so here's some ground current. This is an animation too, but whatever. It's just these negative signs are flowing along up through this person's body up one leg and out the other. And oops, content warning, I'm about to show, sorry, I just sort of did a picture of livestock with burns. This is especially dangerous, this kind of ground current thing is especially dangerous for livestock because there's a big distance between their legs. And here, you should close your eyes if you don't want to see this again, is a cow that has been burned by lightning from the ground current. So lightning didn't strike the cow, it struck sort of somewhere near the cow, and then the current flowed through the ground, up one leg, out the other of this cow, leaving this pretty nasty burn. There's other cool things that result when lightning strikes sand, cool, unlike burning animals. These are called fulgurites. This is sand that is fused into rock by lightning, which I absolutely adore. And I actually have a necklace with a fulgurite on it. So you can buy these things online. Often they're hollow or somewhat hollow in the middle because that's where the most current is flowing, and it sort of turns this sand into glass. And then the rest of it kind of gets fused into rock. Very cool. The ground current that I mentioned you can actually see the results of it. A lot of times you see this at golf courses. So the lightning like struck this golf course pole sticking up out of the landscape, and it burned the ground as it passed. So it left this what's called a Lichtenberg figure in kind of this spread out fractal pattern, just like the kind of fractal pattern that lightning creates coming down from the sky. You can also see it in concrete sometimes. And in people. So I'm going to show some people with minor burns here if you want to look away from that. These are folks that got quite lucky and only have relatively minor burns or lightning scars from being struck by lightning. And you can see again that same fractal pattern as the current tries to find its way to ground. Okay, let's talk about people versus trees. If you remember where I was talking about electrical resistivity, one of the big differences between people and trees, actually there's a lot of differences between people and trees, but in terms of current, one of the big differences between people and trees is our electrical resistance. Current can flow pretty well through a person, through our skin and to the ground, or even through our muscles. We're made out of a lot of water and into the ground. But a tree, turns out, is made out of much less water. So what happens when lightning strikes a tree? Let's watch a little video of that because it's fun. So here is lightning striking a tree. Sadly, this is not at high speed, but check it out. Lightning just struck that tree, and that tree does not have very good current flow. And so as the lightning tried to reach the ground, it lit that tree on fire and basically made it explode. All right, back to talk. Here's another picture, still frame, of a tree just cracking apart by getting struck by lightning. So really depends on what lightning strikes, what the effects are. I'm not going to dwell a lot on the injuries here, but according to the CDC, only about 10% of the people struck by lightning die, and that's usually from a heart attack. This pie chart here tells you kind of where lightning related injuries come from. And it actually, a very small amount of them, this little blue slice here, 3 to 5% of lightning injuries actually come from somebody being like directly struck by lightning. That ground current that I talked about that like hurts a lot of livestock, that's actually about 50% of lightning injuries because the lightning strikes, but then it spreads out and it's got this kind of big area effect. So there's a lot of injuries from that. You can also, like if lightning strikes like a tree, sometimes it'll be like side flash. And if you're near that tree, you can get hit by lightning, even if the lightning actually hit the tree. So like standing out underneath that big tree in the middle of the flat landscape, not a great choice due to side flash. Also, if you're touching that tree and that tree gets struck, the current can flow through you instead of through that tree. If somebody you know is struck by lightning, starting CPR, calling 911, using a defibrillator, those things can be really important to saving that person's life. Also, the biggest element of lightning safety is when thunder roars, go indoors. Don't be outside in a lightning storm if you can help it. However, if you are outside in a lightning storm, this is what you can do, something you can do at least. Crouch on the ground away from solitary tall objects if you can, and you want your feet touching each other. For me, who doesn't crouch a lot, I can do this with my heels touching. And the reason for that is that ground current, if it comes in one foot, it'll go through the other foot out the other foot without like going all the way up and getting your heart and all your internal organs that you don't want to have be fried. You also want to avoid touching conductive materials, and if you can, cover your ears to protect your hearing. But mostly just go inside if you can. Okay, I don't have a lot of time left because I want to leave some time for questions if this is live. And anyway, if it's not live, cool, it's a shorter talk. Other types of lightning. We've talked a lot about regular old lightning, and turns out there are other stranger types of lightning that occur. Here is a little diagram of the ground and then the stuff above the earth. And this is on what's called a logarithmic scale, so you can see that it goes up pretty fast. Each of these blocks is a 10-fold increase. And around here at about 100 kilometers is where the space shuttle is orbiting. And up there, way up in the sky, where the atmosphere is kind of not really so much there, there is some wacky types of lightning called blue jets and red sprites and elves, all this cool stuff, which we don't really understand that well. And I'm going to use time as an excuse not to talk about it, but mostly we don't understand it very well. There's also ball lightning, which is pretty cool, which has recently actually been kind of caught on scientific apparatus, so we can study it a little bit better. But it's super wacky and we don't understand it either. So here's a photograph of red sprites. These crazy things. These are a lightning-related phenomenon that we don't understand very well, but boy, are they cool looking. All right, so that's it for me. I am going to leave you with a plug to buy my book if you enjoyed this talk and if you like lightning. My first novel, Weave the Lightning, was out in April of 2020 from Solaris, and it has some seriously cool lightning magic in it. But don't take my word for it. Shannon McGuire calls it a cutting story of revolution, rebellion, romance, and the sort of strange sorcery we don't see very often. So I'd love it if you'd pick up a copy. Book 2 is coming out in spring 2021. So yeah, thank you for attending my talk, and I hope you learned some cool stuff about lightning. I'm Corry L, signing off.